This video is meant to go over some of the early scientific experiments and laws that came from. I'm going to start with Antoine Lavoisier. He's pictured there with his wife, who also helped him with some of his experiments. Lavoisier developed the law of conservation of mass. So here in the left-hand square, we see reactants that go in, and on the far right-hand side, these two reactants, potassium iodide and mercury nitrate, will react to form the two products on the right. One of them is the white crystalline solid, potassium nitrate, and the other, the orangey one, is a mercury iodide solid. And you can see them being mixed together in that middle square. And so what Lavoisier stated, this is the reaction shown at the bottom, was that the masses of the reactants, when you combine them together, always equal the masses of the products that were formed. And so we know of this now as the conservation of mass. The second one I want to talk about is Joseph Proust. And back in the day, Proust is pictured there on the right, and so his experiments were conducted in the early 1800s. So Proust was able to take a pure compound and decompose it into its elements, and he could measure their masses and determine sort of their percent composition. Okay, so he took a compound that he knew its properties. So compound 1 was a colorless, odorless gas present in our atmosphere, and he could take this and he could decompose it. He knew that it was composed of carbon and oxygen, and he could separate them into the elements, and he determined, based on his 4 different samples, no matter when his samples were collected, whatever the conditions were, he would have different samples, and he always determined that this particular compound was always almost 30% carbon and about 27% carbon and about 73% oxygen by mass. Took a different compound also composed of carbon and oxygen, which was colorless and odorless, but it was toxic to humans and other mammals. And he could decompose that one into its elements, so it's different than compound 1, but also composed of carbon and oxygen. And he discovered that these also, no matter what sample he collected, as long as it was this specific compound with these specific properties, he would get that it was about 43% carbon and about 57% oxygen. So if we move on, John Dalton took those experiments and went a step further and said that not only does compound 1 always have the same percent carbon and the same percent oxygen, and compound 2 always has its given percent composition, but when we compare compound 1 and compound 2 to each other, knowing that they both contain carbon and oxygen, that you'll notice that samples 1 through 4, that they have the same mass of carbon for each, but the mass of oxygen here, when we compare that to the mass of oxygen in compound 2, if you look and see how they are related to each other, compound 1 always has twice as much oxygen for the same amount of carbon. And so now we know that compound 1 must have been carbon dioxide and compound 2 must have been carbon monoxide. So Proust determined that carbon dioxide, no matter how it was isolated, always has the same percent composition. That carbon monoxide, no matter how it is isolated, always has the same percent composition. John Dalton went on to extend that experiment and say that if a compound if different compounds are formed from the same elements, that they often combine in proportions that are ratios, that are integer values, right? So in this case, there's twice as much oxygen in compound 1 as there is in compound 2. And so Dalton went on, he used these findings to develop his atomic theory, which is listed. There are a variety of aspects to this theory. The first one is that matter is composed of small indivisible particles called atoms. Atoms of a given element are the same, and atoms of different elements are different. Atoms of different elements combine to form compounds, and that chemical reactions tend to involve the separation, rearrangement, or recombination of atoms to form new substances. The atoms themselves do not change. No atoms are created, and no atoms are destroyed. And so we, of course, now know that all of these things are true. Some of the pieces of his atomic theory about the indivisible particles called atoms, we could contest that these days, but certainly most of his atomic theory is spot on. Now we're going to do some practice problems. Okay, here's our practice problem. Box A below reacts to form products. Which box or boxes, B through D, represent a product mixture that is consistent with the law of conservation of mass? So here, the yellow and the red are supposed to represent different elements.
The audience, the athletes, the judges, and they have.
And so these red that I'm circling, there are 5 of these, and I'm going to call them A2 molecules. Looks like oxygen to me because oxygen is usually red, but let's just call it A2. We have 1, 2, 3, 4, 5, 6, 7, 8 of these yellow ones, which we're going to call B. Oop, we're calling it Y, sorry. And then we're going to count them down here at the bottom too. So box B, 1, 2, 3, 4, 5. There's only 5 Ys. So that one can't be right because there should be 8 Ys, right? C, 1, 2, 3, 4, 5 Ys here. And here, 1, 2, 3, 4, 5, 6, 7, 8 Ys here. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 A's, which would be 5 A2s. So D is the answer, because if you divide this up into yellow spheres and red spheres, you end up with the same amount. You didn't lose anything. Now if we keep going, number 2, which pair of boxes below illustrate the law of multiple proportions? So we counted here 10, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 red spheres. So remember, multiple proportions just means that they can combine, you know, the same elements can combine in different proportions to give different compounds, right? And then it's going to be a ratio. It's going to be a whole number ratio. And then here we have 5 blues. 1, 2, 3, 4, 5 blues. And then we're going to look at box B. If we do the same thing for B and C and D, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 reds and 1, 2, 3, 4, 5 blues. And down here we have 6 reds, 1, 2, 3, 4, 5, 6 reds, 6 blues, 6 reds, 6 blues. Now, law of multiple proportions says that we're combining and they'll combine in different proportions, right? So the law of multiple proportions states that we're going to make 2 different compounds and they're going to combine in different ratios. And so box B has the reds and the blues combining at a ratio of 2 to 1. Down here, the reds and the blues are combining at a ratio of 1 to 1. And so B and D are sort of illustrations of the law of multiple proportions. The reason why A and C don't match is because these are elements. They're elemental forms. They are not compounds. And so they don't really match with the law of multiple proportions. Now, it might be that they match with the law of conservation of mass, right? It seems like you got 5 blues and 10 reds and 10 reds and 5 blues. You know, A to B is sort of like a conservation of mass issue. That's sort of what number 1 was asking, though. Number 2 is asking about law of multiple proportions, which is a little bit different.